In this second tutorial, we will be using permutations and combinations. So if we flip over to this page of our notes and we're talking about permutations, one of the most important things to remember for permutations is that the order very much matters. The order of the elements matters. So for example, if we're talking about the first three letters of the alphabet, we could take the A, the B, and the C and put them in this order. Or we could say A and then C and then B, and that is a separate permutation. Or we could say B and then A and then C. That's another permutation. Or we could take B and then C and then A. So now we have four different permutations for the first three letters of the alphabet. We could do C, A, B, which is actually the only one that would spell a word. Or we could do C, B, A. There are 6 different permutations if we're taking the first three letters of the alphabet, because each different order matters. So how we can calculate the permutations on our calculator is given by the formula in this box. You don't really need to memorize the formula, although the formula looks a little exciting, doesn't it? It has an interesting symbol called a factorial. A factorial is an exciting part. It's the exclamation point in math. And what that means is we're taking numbers and multiplying each number before it. For example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. That's what a factorial is. Whatever the factorial is that we're taking, we take that number and multiply each number before it all the way down to 1. So actually, if we look at our previous example, the talent show question, we had how many ways can the 10 contestants place? 10 times 9 times 8, 7, 6, 5, 4, 3, 2 times 1 is actually equal to 10 factorial. So we can call that a factorial. So that's interesting. Anyway, so the permutation formula uses the factorials. What we need to know is how to do this on the calculator, and the calculator is math. We have to push the math button, and then we're going to go over to the probability section, which some calculators have just PRB, some have the PROB, and then it's number, actually let's pull up the calculator. I forgot which number it is. If I go to math, and then go over to this calculator has PROB as probability. The permutations is number 2. We can also see that that factorial exclamation point is number 4. So maybe we write that down as well. So the permutation is number 2, and it's the NPR. So what we want to do is we want to type in the N first and then go follow these steps to pull up the NPR and then type in the R. So this symbol needs 2 numbers on either side of it. And just to note that the factorial button is math, and then over to the probability, oops, and then number 4. There's your exclamation point. That's your factorial. Okay, so permutations are when the order matters. Let's ask how many permutations are possible for the letters A, B, C, D, E, and F. So the first 6 letters of the alphabet. This is without repetition. So that means that we cannot repeat the same letters. We can only take 6 at a time. So what we're doing is taking 6 things, and it's a permutation of those things taken 6 at a time. That's what this permutation would be. We have 6 total things, and we're going to use all 6 of them. And that's what we would plug into the calculator. So if we pull up our calc, let me slide it over, and let's clear this out. I'm going to push the 6 first, and then I'm going to go to the math and go to probability, and then down to number 2, And actually on this calculator, it instantly puts the little 6 where it's supposed to go, and then it's asking for the last button, or for the last number, and it's 6p6, and we get 720. So there are 720 different ways to write the first 6 letters of the alphabet. And that's actually the same thing as 6 factorial. If you typed in 6 factorial onto your calculator, type the 6 and then go to press math and then over to probability and it's number 4, 6 factorial is 720. It's the same reasoning as if you think about 6 events, picking these 6 letters, 1, 2, 3, 4, 5, 6. There's 6 ways to pick the first one, and then 5, and then 4, and then 3, and then 2, and then 1. Multiplying all those together does indeed make 6 factorial. Or we can understand that since the order matters, it's a permutation of 6 things using all 6 of them. As opposed to our second question, which is the Appalachian Trail. Example 5, you are making a list of hikes along the Appalachian Trail for this summer. You have 10 available hikes, but you only want to go on 6 of them. How many different itineraries are there? So this time we're still talking about a permutation. This time we have 10 possibilities of hikes, but we don't want to use all 10 of them. We just want 6 of them. So it's 10 total things that we can take 6 at a time. So this is going to be plugged into the calculator as, again, we need to type the first number first, so I'll type the 10, and then I'll push my math and go over to the probability down to the permutation number 2 and end that with a 6. So it's 10p6, and I see that we have 151,200 possibilities. 151,200 different itineraries. So again, it's pretty easy to pull these up on your calculator using these steps. You just need to remember that you're using permutations when the order matters. Let's flip over to our last topic, which is combinations. Combinations, the order does not matter. So if I'm taking the same first 3 letters of the alphabet, A, B, C, I don't care if I write it as ABC or if I write it as BCA or if I write it as CAB. It doesn't matter, excuse me, CAB. All represent one combination. There is only one combination for the first 3 letters of our alphabet. I don't care the order because the order does not matter. So that's what the combination is. It's a different formula, clearly, but it's the same steps in the calculator, except for it's number 3. So if I go to math and go over to the probability, and it's number 3 is what the combination is, the NCR. A lot of mathematicians say choose in place of the C. So back to that hiking example, example 6 now. What if the order you wanted to take your hikes, from example 5 above, did not matter? If the order did not matter, how many distinct hiking trips could we take? This now is a combination. We still have 10 total hikes that we can take, but we're going to choose only 6 of them, and the order does not matter. So if I type this into the calculator, I'm going to be typing the 10 first, then going to my math, over to probability, down to number 3, and ending with the 6. So 10 choose 6. We have 210 possibilities. If the order does not matter, then we have fewer possibilities. It always bugs me when we're talking about lockers and locker combinations in high school, because that's not really what they should be called. Because the combinations, the order does not matter. But I'm pretty sure that for you to get into your locker, you need to put the 3 numbers in the correct order. So we should be calling them locker permutations. I guess it's kind of funny, but it's a misnomer. They shouldn't be called locker combinations anyway. So the combination, the order does not matter. So let's look at these last two examples, and we're going to talk about a deck of cards again. So if you don't play cards, that's fine. I'll tell you anything you need to know about a regular deck of cards. The first example, how many possible 5-card poker hands exist? So poker, if you're playing poker, you usually are dealt 5 cards, and we want to know how many different hands could possibly exist. Well, we need to figure out, first of all, is this a permutation or is this a combination? Permutation, the order matters. The combination, the order does not matter. So if you've ever played cards, I don't care if you've played Uno or Go Fish or if you've played poker, when somebody deals you 5 cards, does the order of the cards matter? Well, the answer is no, because usually what you do when you get those cards anyway is you put them in a different order and you put all the same numbers or the same shapes or the same colors together. So this absolutely is a combination. So there are 52 total cards like we've talked about before, and we're going to choose 5 of them. This will be how many possible poker hands exist. 52, choose 5. Plug that into your calculator and you get quite a few. You'll have 2,598,960. So almost 2.6 million poker hands. That is a lot of possibilities. My last example before we do our final try. Example 8, how many of those 5-card poker hands would exist where all 5 cards are the same color? The same color, not the same suit, the same color. Well, again, if you don't know much about poker or about the regular deck of cards, there are 2 colors. There are 26 red cards and there are 26 black cards. So we're talking about something from the 26. Either they're going to be all 5 are going to be red or all 5 are going to be black. There's actually 2 events. So this is sort of the fundamental counting principle again. There's 2 events happening. The first thing we need to do is pick which color we're talking about. So I'll put that right here. And the second event is picking the 5 cards. So since we know that there are only 2 different colors in our deck of cards, we really only have 2 possibilities, 2 different colors, red and black, and we're going to choose one of them. So this will determine what color we're talking about, and then we're going to multiply that by the number of ways we can pick those 5 cards. Well, there's only 26 of a certain color, and we're going to choose 5 of them. So we need to multiply these 2 combinations together to figure out how many possibilities exist for that. Plugging those both into the calculator and multiplying them, we get 131,560. And I'll put hands. So there's our permutations and combinations. I'd like to, now that you've learned all the combinatorics, I'd like to go back and see if you got the correct answer for try 2. It says answer the original questions. So let's go back to that, all the way back to the beginning, see about those license plates. So we said 3 different letters in any order or 5 different non-zero digits in any order. Now we have the tools to be able to attack this. And I like to use the fundamental counting principle. 3 different letters would be 26 times 25 times 24. That would give me 15,600. Quite a few license plates. And let's see our second one, 5 different non-zero digits. So there's 5 events here. Non-zero means that I can't include 0, so there's only 9 ways to pick the first one, and then 8, and then 7, and then 6, and then 5. And if I multiply all those together, I get 15,120. So this is our big winner, and if you chose A, then you were correct. So thanks for watching these tutorials on combinatorics, and we'll practice this more in class, and I'll see you then. Oh, thanks a lot. See ya.